remember, we had proved, I mean, we have omega n, we know that it converges when n goes to infinity. To omega infinity. Basically, we know that there exists beta c such that omega infinity is positive almost surely if beta is smaller than beta c, and omega infinity is equal to 0 almost surely if beta is larger than beta c. Okay, and a priori at the moment, this is the assumption we have. Okay, and what we are going to prove now is if d is larger than 3, then beta c is larger than 0. Okay, and the proof of this, well, it's due to, well, okay, basically, it's almost the earlier result you can find about directed polymorphs. It appears in a paper of Imbrie and Spencer. I mean, of course, the existence of beta c was only proved in the 2000s, but what this result says is that if beta is small, then you have weak disorder. Okay, so yeah, so what's the idea here? We show that if beta is small, then the supremum over n of the expectation of Wn beta omega square is finite. Okay, so if our sequence of variable is uniformly bounded in L2, well, it means in particular that it's uniformly integrable. Okay. So, okay, let's prove this. So you will see that this is not super complicated because you can compute, you have an explicit expression for this, which is easy to work with. So, okay, first thing you want to do is, well, this Wn is the expectation of something. So Wn squared, you can write it as the expectation of, okay. Well, perhaps x1, x2. Just okay, so what you get here is, well, the exponential of the sum from n equal 1 to n. Then you get beta. Okay, I think. Okay, let's forget some brackets because if not, this will be really confusing. Omega n x n 1. Plus omega n x n 2 minus 2 lambda beta. Okay, so here you have brackets around this. Okay, but I think I will just fall. Okay, I don't know. Okay, so you have 4 brackets in there. Okay, and then, okay, you can do Fubini and I give myself the right not to repeat the writing. So now, okay, you're taking the expectation of something. The expectation is, well, if you look at the sum in small n, okay, well, it's a sum of independent random variables. Okay, so you can just factorize. So the only thing you're interested in is really what's the expectation of this thing. For a fixed trajectory x. Okay, and well, the value of this, it really depends on something. It depends on whether the spatial coordinates here are equal. Okay, so you have 2 choices, basically. Either xn1 is equal to xn2, and in that case, you get exponential 2 lambda beta. Sorry. Lambda 2 beta. Okay, remember that lambda is a log Laplace transform. Okay, and in the other case, well, you get the Laplace transform to the square, so you get exponential 2 lambda beta. Okay, so I will set chi beta, which is equal to lambda 2 beta minus 2 lambda beta. Okay, perhaps. Yeah, okay, let's set it like this, okay. And what you get here is just, well, a factor exponential chi beta for all the coordinates n such that these 2 things are equal. Yes. Yeah, I mean, this is the only thing you can okay, the blackboard P or blackboard E, it's always used with respect to omega. And here, I mean, this is the only thing you have. Okay, and here what we have done, the first thing we have done is Fubini. Okay, so what you get here is that E of W and beta omega square, well, it's equal to, and here, okay, I get exponential chi beta sum from n equal 1 to n indicator xn1 equal xn2. Okay, I mean, when things are different, this thing is just canceling with that. Okay, so so in particular, if you take, well, the limit when n goes to infinity of E wn beta omega square, well, it's equal to chi beta L infinity, where L infinity, well, if you it's the number of time that xn1 and xn2 meet. Okay, I mean, this is just monotone convergence theorem. Okay, yeah. Okay, chi beta is positive. Okay, just by Jensen. Okay, the expectation of the square of this is larger than the square of the expectation. Okay. So now, if you remember our second class, okay, well, okay, let's look at yn, which is xn1 minus xn2. Okay, and the probability that 1 yn is equal to 0, this thing is equivalent to some constant, okay, which we could compute, but times n to the minus d over 2. Okay, this is just because this is a d-dimensional random walk, okay, with a support which is truly d-dimensional. Okay, so this is where it comes to be convenient when we prove Polya's theorem to prove it with some bit of generality, because this is not exactly the simple random walk. Okay, so therefore, if d equal 1 or 2, well, we have that the expectation of L infinity is equal to infinity. Okay, so the limit when n goes to infinity of the expectation of Wn beta omega square is equal to infinity. Okay, it doesn't tell us that we have strong disorder, but it tells us that our idea to prove that you have weak disorder by showing that you're bounded in L2 cannot work. But if d is larger than 3, okay, then, well, the expectation of L infinity is finite, and you have that, well, I'm sorry, I should put, yeah, this is very bad. I should put this everywhere, sorry. Because, okay, no, sorry. E and you have E that L infinity is equal to K. Well, this is just equal to PD to the K 1 minus PD, where PD is equal to, well, the probability that L1 is larger than 1, L infinity is larger than 1, which is equal to the probability that there exists n larger than 1, such that xn1 is equal to xn2. Okay, again, this is what we have proved in our second lesson. This thing is a geometric random variable. Okay, so therefore, what you have is that the limit when n goes to infinity of W beta omega square, Well, it's equal to the sum from k equal 1 to infinity, 1 minus PD. PD exponential chi beta to the power k. Okay, I'm just. Therefore, it's finite if PD exponential chi beta is smaller than 1. Okay, it's finite if and only if this is true. Okay, and this kind of ends up the proof because chi beta, I mean, it's continuous and it's equal to 0 when beta is equal to 0. So this is finite if beta is sufficiently small, just by continuity. Okay, but let me elaborate a little bit on this. So any question about this proof? Okay, so yeah, let's call beta 2. Okay, the well, if you want, the supremum of the set of betas such that beta PD exponential chi beta is smaller than 1. Okay, so what the result says is that beta c is larger or equal than beta 2. Okay, if beta is smaller than beta 2, then this has to be true. Okay, and no, sorry. Okay, I mean, this is the same thing, but I have not proved it yet. So if beta is smaller than beta 2, then this has to be smaller than 1, and therefore. Okay, so and yeah, when if d larger than 3, what we have proved is that beta 2 is positive. Okay, so yeah, first thing to remark is that beta 2. Okay, if beta is larger than beta 2, then PD exponential chi beta is larger or equal to 1. Okay? And in fact, what you have is that PD exponential chi beta 2 is equal to 1 if beta 2 is finite. Okay, and the second thing is that if the probability that omega 1, 0 equal to m is equal to 0, okay, where m is the essential supremum of omega 1, 0. So in particular, this is true if your distribution has no atoms. This is the reason why then beta 2 is finite. Okay, okay, and in fact what we are going to show is that beta 2 can be infinite, okay, when this is not satisfied. Okay, so there are some, yeah, we have not really proved that you have a phase transition in dimension 3. It's possible if omega is as a distribution with atoms, it's possible that you have weak disorder for all betas. But you will see later that it cannot be the case if this is not true, okay? And this is kind of the first indication. Okay, so what do these... Okay, so this is a lemma. Okay, so about lambda beta. So, okay, beta, lambda beta is convex. This is A. B, chi beta is increasing in beta. Okay, and by increasing, I really mean increasing, not non-decreasing. And C, the limit when beta goes to infinity of exponential chi beta, it's equal to 1 over the probability that omega 1, 0 is equal to n. Okay, and remark that I've taken the assumption that omega is bounded from the beginning. For most of the things I say, you don't really need that. Okay, but what you always need is you need lambda beta to be finite. Okay, so the standard assumption in the literature is that lambda beta is finite for all beta. Okay, and most of what I said is valid under these assumptions, but sometimes it's convenient to have bounded environments, so this is the reason why. Okay, so let's prove these things. You see that, yeah, from B, okay, you're deducing this part here. Okay, this is from B. Okay, and this thing is from C. Because this thing implies that exponential chi beta goes to infinity, so at some point this will be true. Okay, so this set is not empty. Okay, this being beta 2 being equal to infinity means that this set is empty. Okay, so let's start with A. So this is just Hölder's inequality. So take alpha in 0, 1. Okay, what you get automatically is that this is smaller than, okay, so omega 1, 0, omega 1, 0. Okay, let's put x here, okay? Like that's a generic, okay, z, okay? That's a generic random variable. Because this is true for any variable which is such that the Laplace transform is bounded. Okay, this thing is smaller than exponential beta 1 z to the alpha, exponential beta 2 z to the 1 minus alpha. Okay, this is just Hölder with exponent p and q that are 1 over alpha and 1 over 1 minus alpha, respectively. Okay, so now if you take the log, well, this is lambda alpha beta 1 plus 1 minus alpha beta 2, which is smaller than alpha lambda beta 1 plus beta plus 1 minus alpha lambda beta 2. Okay, there is another way you can see this, but which has basically the same proof, but it's a more general result. What you can say is that, well, if you look at the exponential function here, okay, so okay. This thing, if you look at it as a function of beta, okay, it's a function whose log is convex. Okay, the log is just a linear function, and linear functions are convex. So this is what you call a log convex function. Okay, and expectations of log convex functions are log convex. Okay, and the proof is basically the same. So, and well, it's not true for log concave function, for instance. So you have to be a bit careful. But here, I mean, it's really basically because you have the combination of two things that works together. Okay, so this is A. B. Well, B. I mean, if this is defined for every beta, then it's differentiable. It's infinity. So you can just differentiate. You have that psi prime of beta. It's 2 times lambda prime 2 beta minus lambda prime of beta. Okay, which is positive by convexity. Okay, and in fact, it's strictly positive. Just because you have strict convexity.
But then it's missing for beta positive.
Yeah, okay. But this is sufficient for what we want. Okay, and what about C? Well, C, if the probability that omega 1, 0 is equal to m, if this is positive, then you have that exponential lambda beta. Well, okay. Okay, we'll consider that m is equal to 0. Okay, this doesn't, I mean, you can just shift everything by m, and it doesn't change the value of chi beta. Okay, just because it changes basically lambda 2 beta by 2 beta m and lambda beta by beta m. So we can consider this. So if this is positive, then what you have is that the limit when beta goes to infinity of exponential omega beta omega 1, 0. Well, just by the dominated conversion theorem, this is equal to p omega 1, 0 equal to 0. Okay, and the result follows because okay, because here you have one expectation divided by one expectation squared, and both converge to the same limit. Okay, so now the case which is left is if this is equal to 0, okay, so then what I can do is say, okay, then I can say that this thing is equivalent when beta goes to infinity to this. Okay, I'm assuming that 0 is the essential supremum. Okay, so this means that this decays to 0, okay, if I am assuming this, but not exponentially fast in beta. Okay, and here what I'm taking away decays exponentially fast in beta. Okay, so therefore, here I'm keeping the main part. Okay, so I can write this thing as the ratio of exponential 2 beta omega 1 0 indicator omega 1 0 larger than minus epsilon divided by indicator omega 1 0 larger than minus epsilon and here I have a square and this thing here, so now if I show that this thing goes to infinity, I'm done. Okay, and this last thing, okay, this is, okay, I will not show that it goes to infinity. I will show that it's larger than something which can be made arbitrarily large when epsilon goes to 0. Okay? So the point here is that I can rewrite this thing as 1 over the probability that omega 1 0 is larger than minus epsilon. Beta omega 1 0 beta omega 1 0 square. Okay, I'm writing conditional expectations. If I'm writing conditional expectations, basically, okay, what I'm taking away is just this probability, but I'm having it squared on the denominator. So this is the reason why it appears here. Okay, and now I know that this is larger than 1 by Jensen.
There's not. Is there the square of
Okay, so I mean, basically, I knew that things were larger than 1 from the beginning by Jensen. What I'm doing is I'm using Jensen on a very small part on the part of the space in order to make sure that they are larger than something big. This is just. Okay, so this finishes what I had to say about this theorem, and now we are going to explore a little bit what happened in the weak disorder phase. So yeah, perhaps it's a good time to make a small break, and we resume in 5 minutes. before talking about weak disorder, a last remark about this result, which is kind of a comment on the question you made last time. Can we... beta c is larger or equal to beta 2. Yeah, the question last time was, can we identify beta c? And okay, so what has been the... So there has been a conjecture in the literature. I won't give you any names, but okay, so beta c was equal to beta 2 with heuristic argument, you know. But shortly afterwards, this was disproved. Okay, so in 2010, I would say. So soon. I think this is 09 or 10. Can perhaps. And Berger and Toninelli around the same time. Okay, they prove that beta c is strictly larger than beta 2. So, okay, this simple, I mean, beta 2, it's easy to compute, but it's not equal to beta c. Well, this is not the end of the story. Somehow you can ask yourself, okay, beta 2 is the point at which you start to be non-L2, okay, in the limit. It's the point at which W infinity starts to be non-L2. So you can look at beta p, okay, which is the infimum of beta, yes, such that the supremum of n larger than 1 e w n beta omega p. Okay, because this is the martingale, this thing is increasing in n, okay, because of Jensen inequality. Okay, p larger than 1. You can define this equal infinity. Okay, and what was proved more recently by Stefan Jung, okay, and basically is that beta c is strictly larger than beta p if p is strictly larger than 1 plus 2 over d. And in fact, beta c is equal to beta 1 plus 2 over d. Okay, so really, okay, so this is not yet proved, but basically you can imagine that this beta p it's actually really an increasing function of p. Okay, so it's different for every values of p up to this special value 1 plus 2 over d. Okay, because of course this thing here, it implies that beta c is equal to beta p if p is between 1 and 1 plus 2 over d. Okay, but like moments of order 1 plus 2 over d, they are kind of hard to compute. So. Okay, and of course, I mean, all of this is also true in dimension 1 and 2, but this is only relevant in dimension 3 because in dimension 1 and 2, it had been proved much before that beta c is equal to 0. Okay. So, yeah, now let me tell you something about the weak disorder phase. Okay, so see, it was important to do this before telling you anything. Yes?
I didn't understand how we concluded that beta c is greater than beta 2.
Well, okay. If you're uniformly bounded in L2, then your martingale converges in L2. Okay. I mean, if you're uniformly integrable, okay. So even if this is true, sorry. Yeah. So if this soup is finite, okay, for any p larger than 1, then you're uniformly integrable. So your martingale converges in L1, meaning that the expectation of W infinity is equal to 1. And yeah, so therefore you know that your limit is non-degenerate. And then you have this the 0-1 law that tells you that if it's non-degenerate, then it's positive almost surely. Any other question? This is a problem when you work on a subject for a long time. Things are so natural that you forget to remind them to your audience. Okay, so what about the weak disorder regime? Okay, so proposition, if weak, okay, so perhaps I'm going to define Pn, which is the average measure. Okay, so our goal is to show that this measure behaves like the simple random walk. And perhaps the first thing to do is to show that the average measure behaves like a simple random walk. And this is what we are going to explore today. And so the proposition is the following. The proposition says that basically, well, not Pn is in a sense, well, it's absolutely continuous with respect to the simple random walk, which tells you nothing, basically, because, I mean, you know that this affects only the first n increment, so, but it's uniformly continuous, absolutely continuous uniformly in n. Okay, so proposition, for all epsilon positive, there exists delta such that for all a in G, Pn a smaller than delta, okay, for all a in G, for all n larger than 0, Png a smaller than delta implies that, no, P a smaller than delta implies that Pn a smaller than epsilon. Okay, so equivalently, okay, so what is G here? G is just sigma of x n larger than 0. Okay, the sigma algebra associated with a simple random walk. Okay, so another way to say this is if P of an, okay, P of ak goes to 0 when k goes to infinity, then lim of sup Pn a k when k goes to infinity equals 0. Okay, it's a standard calculus exercise to show that these two things are equivalent. Okay, just to play with delta and with the deltas and epsilon. So we are going to prove this version. Okay, and perhaps okay. So this basically tells you that any event which is typical for a simple random walk is typical for Pn. Okay, so okay, these tell you, for instance, that okay, Pn xn larger than square root of n log n, or goes to 0. Okay, or Pn xn smaller than square root of n divided by log n. Okay, and log n is just any function going to infinity. This also goes to 0. And I mean, you can say things that are a bit finer, like if you're taking an event which concerns the random walk up to time n. Okay, so for instance, you can say, okay, I'm not giving you an example, but your event ak will be something like your renormalized trajectory doesn't look like a Brownian motion. Okay, well then you know that Pn of that will be small. Okay, so you take any property of Brownian motion, well, it has to be approximately satisfied under Pn. Okay. Okay, so the proof of this is the proof of this proposition is in fact super simple, but you see that it's already a strong result. On the other hand, it doesn't tell you anything about localization yet. Okay, because for instance, like you can average random measure and get the simple random walk and have your random measures that are really singular with respect to simple random walk. I mean, for instance, if you take the simple random walk, you can look at it, or if you look at the simple random walk up to time n, well, okay, the simple random walk you can see that as an average of Dirac measure on single trajectories. Okay, so so this does not tell you that this trajectory is not singular. Okay, you need something more. Okay. So what's the proof of this? Well, okay, let's look at Pn of A. Well, it's the expectation of Wn beta omega A over Wn beta omega, where, okay, this thing is almost the definition of Wn beta omega of A. Okay, so this by definition here, this thing is just Wn beta omega p and beta omega of A. Okay, and this is equal to the expectation of the exponential. And here you put this indicator of A. Okay, it's just your partition function, but restricted to the event A. Your normalized partition function, but you restrict it to the event A. Okay, so if you want Wn here implicitly, I'm just considering it as a measure. Okay, and Wn of nothing is just the total mass of the measure. Okay. And then I can say, okay, this is, I have two possibilities. Either this is larger than delta, or this is not. Okay, either this is larger than eta. Yeah, either this is larger than eta, or this is not larger than eta. Okay, so this is yeah, what can I say? Okay. Yeah, so this thing here, it's always smaller than 1. Okay, so okay. On this event, I'm just bounding this by 1. And on the complementary event, well, I'm saying, well, this is larger than eta. So this thing is smaller than 1 over eta. So eta to the minus 1 times the expectation of W and beta omega A. Okay, and well, good news. The expectation of W and beta omega A, well, if you look at it just by applying Fubini, okay, well, this indicator of A, I mean, you can put it outside, okay? And the expectation of the exponential, it's equal to 1. So this is just P of A. Okay, so the very good thing about non-normalizing, I mean, you don't get a probability, but you get something which, on average, is exactly the simple random walk. Okay, so this is good. But we want to have something that does not depend on A, or on N, on the right-hand side. Okay? Because we want something which is valid for all N, so basically we don't want our bound to depend on N. So Pn of A, well, you can say that it's smaller than, okay, the probability that the infimum of W and beta omega over all N larger than 1 is smaller than eta, plus eta minus 1 P of A. Okay? This is a bigger event. Okay? And now the good thing is that this thing, okay, this is positive almost surely. Okay, why? Because, well, this Wn is positive for all N, and the limit is positive almost surely, so the infimum has to be positive. Okay, so therefore, this probability here, it's smaller than epsilon over 2 if eta is small. Okay? I mean, the fact that it's positive almost surely, it means that this thing goes to 0 when eta goes to 0. Okay, and then you take delta to be, well, the usual thing, like eta epsilon times epsilon over 2, and you're done.
Get why the infimum is positive.
Well, it's just something, okay. If an goes to a infinity, okay, so you have this. Again, positive for all n larger than 1, or larger than 0, whatever, and a infinity positive. Then you know that the infimum is positive. Okay? Just like first year calculus, I guess. Like you're larger than a infinity over 2 after some time, and before you're positive because you just take the infimum over finitely many values. Okay. So very good. So we are going to do basically something else. We are going to try to explore infinite volume measures. Okay, so to see how when you are in the weak disorder, instead of, well, you can show that this measure here, it converges to something when n goes to infinity. Okay. Well, this convergence, in fact, holds in the, okay, we will see in which sense this convergence holds. But before that, let me make a comment, some kind of historical comment. So using a variant of this argument, okay, you can show something which is well, stronger, but with a stronger assumption. So you can define some different measure. Let's call it Q. Okay, Q. Okay, Q of B. It's equal to the expectation of Pn beta omega times Pn beta omega of B. Okay, for B in G. Okay, and what you can show is that, okay, Qn. And what you can show is something similar here. Okay, you can show that Qn of B is absolutely continuous with respect to, okay. Qn. Oh, Qn of B smaller than delta implies that P of B is smaller than epsilon in the same way. Okay, but you can, what's easy to prove is that this is true if beta is smaller than beta 2. Okay, and somehow this, for instance, implies that you don't have localization. Okay, because you can take as an event B, well, what's the probability that my two endpoints, if I take two copies of the polymer, they share the same endpoint? Okay, so if I have some atoms in the endpoint distribution, then this probability would be positive. Okay, and well, averaging with respect to the environment, I mean, if for a positive fraction of the environment this is positive, then this average would be positive. But here you know that this probability is, well, decays like n to the minus d over 2. It's the opposite, right? It's the opposite. Okay, so this is smaller than the n to the minus d over 2, so this has to be small. Okay, so therefore this tells you that your endpoint measure is delocalized. Okay, and the reason why you need beta smaller than beta 2 is, yeah, here when you want to take the expectation of some Wn square of b, okay, well, you will, yeah, basically for this to be even finite, okay, the equivalent, well, you need beta smaller than beta 2. Okay, so this is the reason why historically results were first proved under this assumption. Okay, so basically the summary is, yeah, you can have a result which is an extension of this result where here you have two copies of the polymer measure, but at the cost of having a stronger assumption on beta. Okay, so now let me tell you about the infinite volume measure. Any questions so far? Okay, so it's not very central for directed polymer, but it's a general topic in statistical mechanics. I mean, you start to define things on a finite volume, and then you want to know whether you get some limit behavior when n goes to infinity. So you kind of want to look if you can define this measure when n is equal to infinity. Okay, and here somehow there is something very natural you can do. So you look at, you fix A, okay, a measurable event, and you look at this thing, and you say, okay, I know that my denominator converges to something positive. So what about the numerator? Perhaps it converges, and then this thing will converge. Okay, so if you look at the numerator, Wn beta omega, well, this thing is a martingale. Why? Well, exactly for the same reason as when you don't have the A. I mean, if you remember the argument, okay, if you remember the argument, sorry, what we did was to apply Fubini And when you apply Fubini, I mean, immediately you can take the indicator away. So. Okay, and once you've done that, well, you're pretty much done. I mean, basically, you take the first n terms of the sums out, and the last one, it's independent. So. Okay, it's a martingale. Is it uniformly integrable? Well, yes, because we know that Wn is uniformly integrable, and Wn of A, it's smaller than Wn. And it's larger than 0. Okay, so so what you have is that, well, you can define, okay, if you want, P infinity beta omega A is equal to the limit when n goes to infinity of P and beta Okay, this is very good, and then I mean what you've really defined, okay, is a collection of random variables that are indexed by G. Okay? Well, is it an infinite volume measure? Not really. So why? Well, simply because here you've defined this, okay, as a collection of random variables. So as a basically as a process indexed by G. But the problem is that you have to remember what's a random variable. And the random variable is actually not exactly, it does not correspond to the definition of random variables you're given in the beginning of the class of probability. I mean, the first thing you do in probability is forget about this definition and substitute it with another one, which is you're considering random variable modulo modification on a set of measure 0. Okay, so yeah, this thing is defined only. This thing is defined only on omega A with P of omega A equal to 1. Okay, so if you want to look at this as really functions defined on your state space, well, okay, like this would be formally defined on the intersection over all A in G of omega A, and this might very well be empty. Okay, so it doesn't mean that this doesn't make sense, but really it's a collection of random variables indexed by G, where by random variable you really mean, yeah, a class of equivalence of random variable modulo modification on a set of measure 0. Okay, and after all these considerations, it doesn't make sense to ask the question, is this a probability measure? Because for a probability measure, you need some properties to be verified simultaneously for all A. Okay, so is there a way to get out of this mess? Well, yes. So basically, what we can do is, well, first define this on a countable subset of G, okay, and then extend things by anything you want. So I will use Kolmogorov extension principle, but it's really an overkill. You could use Kara-Theodori's extension theorem, but you have to be a bit careful when you do that. Okay, so let's call Gn the sigma algebra generated by xn n equal 1 to n. Okay, and Gn is finite. Okay, well, depending on how you consider things, it might be finite or countable, but it doesn't really matter. So what we are going to do is define P infinity beta omega of A for A in the union of Gn. Okay, and so this thing I call it A, and I call it A because it's an algebra of set. So yes, and because this thing is countable on this algebra, you can easily show that this is okay. This is an additive. Okay, so on A, we have P and beta omega A union B equal P infinity beta omega A plus P infinity beta omega B. Almost sure. Okay, for fixed A and B, it's just the fact that this is satisfied for every n, so this has to be satisfied on the limit. And then, yeah, because A is countable, well, it's also true almost surely simultaneously for every A and B. Okay, so this is good. So to extend it, you would just need to prove sigma additivity, or actually, yeah. So you just need to prove sigma additivity, and to prove sigma additivity, you actually only need to prove continuity from above. Okay, so what you just need to prove. So additionally, we have that if an is increasing, then P infinity of the union when n equal 1 to infinity of an is equal to the limit when n goes to infinity of P infinity of AN. Okay, so okay, this thing plus this thing, it guarantees that you're sigma additive, and therefore you can use Kara-Terodori extension theorem to extend P infinity to G. Okay, so why is this thing true? Okay, this requires a proof. Okay, so here, okay, if you remember well your measure theory, basically here is the only thing you have to show that you don't gain something at infinity. Okay, so you know that P infinity of the union when n equal 1 to infinity of AN, you know that this is larger than the sum from n equal 1 to k of P infinity of you know that this is larger than this. Okay, for every k. So therefore, the only thing you need to show is that if A is equal to this union, the only thing you need to show is that the limit when k goes to infinity of this goes to 0. Okay, so this is not too hard to prove because this thing is by definition, okay, the limit when n goes to infinity of P Okay. Yeah. So the point here, okay, the important point here is that this is a decreasing limit. Okay, so if you want to prove that it goes to 0, here we want to prove that it goes to 0 almost surely. But you only need to show that it goes to 0 in probability, which is good. Okay, so now what you're looking at is really this thing. And by phi2, okay. So by phi2, what you have is that the expectation of P infinity A k, well, it's smaller than the lim sup when n goes to infinity of the expectation of Pn, the lim inf, sorry, but it doesn't matter, of Pn A minus AK. Okay, and well, this is exactly Pn A minus AK. Okay. When k goes to infinity, this goes to 0. Okay, so I erased the result, but we have a result that tells you that the soup over n of this goes to 0 when k goes to infinity. So this is. Okay, so you can use Kara-Theodori extension theorem. Okay. Extends P infinity beta omega to A to G. Okay, so yeah, to finish, I would like to do basically two comments. So first thing is that this infinity volume measure, it's not something which is crazy complicated. Because you can write explicitly what it is. Okay, you have a simple expression for it for elements of A. Okay, and knowing this, basically, you can compute the transition probabilities corresponding to that measure. So this under P infinity X is not a Markov chain, but it's a bit like a Markov chain. It's just that the transitions probabilities depend on the time you're considering. Okay, so it's what is called a time inhomogeneous Markov chain. Okay, meaning that, yeah, where you are at time, where you your position at time n plus 1, it depends only on where you are at time n plus on the value of n. Okay, so for this reason, basically, this is the reason why Kara-Theodori here is a bit of an overkill, but I will need this result, or just a variant of this, for the last thing I want to say to you afterwards. So this is the reason why I wanted to tell you about this. Any question? So let's look at the event x1 equal x1, xn equal xn, okay, xn equal xn. Okay, because any element of Gn is a finite union of this kind of stuff. Okay, okay, here I'm just considering that also that x1 is a neighbor of 0, and this is a nearest neighbor path. Okay, because if not, so what's the probability of this? Well, it's a quotient of two things. So what I have on the denominator is this. And what I have on the numerator, well, I have first it's small x, I guess. Well, the weights collected by the trajectory up to time n. And then I have, okay, I have also 1 over 2d to the n, which would be the probability of such a thing under the original measure. And then I have to multiply by something, which is just theta n xn w infinity beta omega. Okay, it's just the sum of, I mean, here basically what you want to write is the sum over all trajectories that start with this, or like the expectation, okay, over all trajectories that start with this, of the infinite exponential here when I have infinity here. So what I would do is I put in factor what I have in common to all the trajectories, and the rest is, well, okay, it's only a formal equality, but This is what you get. Okay, and if you want to check this, you just have to show that. Let me put an n plus m here, and then you have m, and then you have n plus m. Okay, so this is like. So with infinity, okay, there is something to prove, but with m, this is trivial. And then you take m to infinity, and you get the statement you want. Okay, and then from this, okay, you get your conditional probabilities. Okay, you see that p infinity x n plus 1 equal y, knowing everything. Well, it's knowing x n equal 1 to n. Well, you can write it as some function. Okay, like p omega n plus 1 y xn. So you can write it as for regular Markov chain, okay, except that here your p also depends on it. Okay, and I don't want to write the expression for this, but you can get this from there. Okay, it's just a ratio of, you have a exponential of here what you have at n plus 1, and then you have ratios of partial functions. Okay, and like if you're given transition like this, you know, like if you want to show that Markov chains exist, basically there is a construction using only uniform 0-1 random variables. Okay, and this construction works also there. If you have all these transitions, so for this reason you don't really need Kara-Theodori. Okay, you can use this construction to have already some extension. Okay. Okay, and also uniqueness of the extension. Okay, so perhaps the final comment yeah, the penultimate comment, in fact, because I have something I forgot to say 1 hour ago. But the penultimate comment is that somehow this was the right idea, even if it doesn't work, because okay, so now, I mean, the definition of P infinity is the probability that extends what's defined on A. Okay, so let's write it. Proposition, let P infinity beta omega the unique probability on G that extends okay, limit when n goes to infinity of we define this thing, which is a sigma additive functional on an algebra. Then for all A in G, the limit when n goes to infinity of Pn beta omega A is equal to P infinity beta omega A. Okay, so what does this mean? Well, okay, it might, for those who have studied Brownian motion, it might remind you of what happened in the beginning when you construct Brownian motion. So this is defined as a stochastic process, so just as a collection of random variables. Okay, and because each of these random variables is defined modulo a set of probability, modulo modification on a set of probability 0, well, you cannot really talk about things that concerns everything at the same time. But then comes the notion of modification of a process, and you say, well, you have a modification of a process basically if these things are in the same class of equivalence, okay, with respect to this modification. And what this proposition says is that, well, there exists a modification of this process, which is a probability measure. Okay, so the proof is just a use of the monotone class theorem. So you just look at M, which is the set of A in G, such that the limit when n goes to infinity of P and beta omega A is equal to P infinity beta omega A. P almost surely. Okay, it's a set such that this thing has probability 1. Okay, and by definition, okay, A is included into M. So what we just need to show is that M is a monotone class, and we are done. So M is stable by complement and finite. Okay. And disjoint finite unions okay, just because okay, I think you just need that it's stable by complement here. Because Pn and P infinity are probabilities. So the only thing we have to show to conclude is that M is stable by increasing union. And yeah, you can trust me on that because I've checked what was the monotone class lemma before I wrote that. Okay, so yeah, why is this true? Okay, so let's take AK that grows to A. Okay, so what I just mean is that this is an increasing sequence and that the union is equal to A. And what we have to show again is really that the lim sup of P when n goes to infinity, okay, of the limit when k goes to infinity of Pn A minus AK, and here I can take the sup over n. Okay. Okay, what do we know? Yeah, I think Okay, well, I think this is really what you want to show. Okay, why is that? Well, simply because you already know, okay, that, okay, this is a probability, so this is increasing, so you already know that the limit when n goes to infinity, when Pn of Pn, you know that this is larger than P infinity ak for every k. Yeah, so you already know that it's larger than P infinity of A. Okay, so what you really need to check is that this thing doesn't make you gain anything. Okay, and this is the same idea as before. So you want to show that this goes to 0. Okay, so you know that this is a decreasing sequence. Okay, so you just need to show that the expectation of the limit when n goes to infinity goes to 0 when k goes to infinity. Okay, and I think yeah, now you can use Fatu, right? The expectation of the limit here, this is smaller than the lim_inf of Pn A k. Okay, and well, now you can make this arbitrarily small by making k large, just because of the first thing we. Okay, and yeah, basically from this statement, what you can get, if you're into that kind of stuff, is that well, the Pn actually converges to P infinity almost surely for the weak topology. When well, it converges weakly, and when you say it converges weakly, it means that you're considering a topology on the set of trajectories, and the topology you're considering is a product topology. Okay, so if you're taking any continuous function on the set of, I mean, basically, the expectation of any bounded continuous function converges, and this is simultaneously for all continuous functions. Okay, just by, I mean, basically, it converges for one continuous function. Well, simply because, well, this is, I mean, if this is true for this, then you can prove, using the usual argument that this is true for simple function and then for measurable functions. So for an individual bounded continuous function, this is true. And then to show that it's simultaneously true for every, basically, you have this portmanteau argument that it's sufficient to check it for a countable dense set, in a sense. Okay, so this works on R. Our space is basically R. Okay, in terms of complexity, this is not more. Okay, because like it's z to the power n. Okay, I mean if you look at the increments, it's actually 2d to the power n in terms of cardinality. So it's really R. Okay, so yeah, I told you all that was good about these results. Now let me tell you what's a bit frustrating. So in all that we have said, basically, okay, so we've defined the infinite volume measure. And yeah, what we have as a consequence is basically that if you take the average of this infinite volume measure, it's continuous with respect to the simple random walk. But actually, this measure here, it's very, very singular with respect to the simple random walk. So let's take an example. And for this, I will just go back to Pn. Okay, so the average of Pn is close to the simple random walk. But Pn individually, it's very singular. So let me give you an example of an event that has a very large probability under Pn beta omega, but a very small probability under the original measure. Okay, and okay, I'm going to consider here, it's not necessary, but I'm just considering that the expectation of omega 1, 0 is equal to 0, so that my variables are centered. Okay, okay. So what's an? Well, so to make these things work, okay, you have to choose an event that is defined in terms of omega. Okay. So an of omega, well, this is a set of trajectories such that the sum from n equal 1 to n of x n omega n x n, and I want this to be larger than n times lambda prime beta over 2. Okay, so remember lambda is convex. So and lambda prime 0, it's the exponential, the expectation of omega 1, 0. So our function lambda is like this. So lambda prime of beta is positive in particular. Okay, this is just derivative of under the. Okay, so P of A and omega well, okay. Let's look at the expectation of this. Okay, if you want to show that this is typically small, let's show that the expectation is small, and then we can use Borel-Cantelli to show that, in fact, it's small for every n, for instance. So what's the expectation of this? Well, you can use Fubini here. So it's the same as the expectation of the probability that the sum over n equal 1 to n of omega n xn is larger than n lambda prime beta over 2. Okay, I mean, when I'm writing this, this is just the double expectation of an indicator. So I can just switch these things. And now I'm looking at this as the probability over omega, so of something concerning omega for a fixed trajectory. These variables, because x is fixed, they are IID. They are of mean 0. So by the law of large number, and well, you know that this thing here is going to 0. In fact, okay. If you know just a little bit about large deviation, okay, you can show that this is actually, this decays to 0 exponentially fast. Okay, but if you don't know it, just say that it goes to 0, and this is already something. Okay, so now let's check that AN is typical under the polymer measure. So, well, you can do the same thing. So if you look at P and beta, well, let's look at perhaps, okay, no, let's P and beta AN. P and, okay, beta. Okay, well, you have, okay, and you look at the expectation, but, okay, well, this thing, okay, and omega, okay, this is 1 over Wn omega beta, and this thing is just a constant. It's bounded between two constants, so I don't really care about it. And then I have my expectation. Tá. Vamos acabar. Vamos acabar.